All right, folks, welcome. Thanks for joining us in this panel session, Grokking Lossless Compression. Someone came up and said, what's Grokking? And it's really making sense of lossless compression. So I'd like to introduce our panel out here. Or maybe you guys could do a brief introduction. Why don't we start right from this side?
Hello, everyone. My name is Andrew Charlakis. I'm a co-founder and CTO at ZeroPoint. My background is in CAS and memory architectures and data compression.
Hello, everyone. My name is Heiner Litz. I'm an associate professor at UC Santa Cruz. I'm leading the Center for Research in Storage Systems there, being a director and doing exciting work across the stack from hardware to software to compression.
Good afternoon, everybody. I'm Scott Shadley. I'm currently at Solidigm working in security and computational storage, and I also sit on the SNIA board of directors. This is my 9th or 10th time now at this event since I've been having fun being a board member and participant, and looking forward to the rest of the week as well.
I'm Mats Oberg. I'm Associate Vice President at Marvell, where I work on signal processing for any storage related, as well as machine learning and computational storage. I'm also involved in computational storage within SNIA.
Hello everyone, I'm Pulkit Jain. I am part of AMD's Adaptive SoC division. I'm an SoC architect there, and my interests are in memory subsystem and system caches.
Fantastic. So quick introduction to myself, Nilesh Shah, and I'm with ZeroPoint Technologies, driving business development. So what I'd like to do is, I have a few questions that I prepared for the panel. I'd like to make this an interactive session. So maybe what we'll do is, I'll start off with a few questions, and then maybe midway we'll open it up to the audience, because I don't want to wait till the end in case we run out of time. So I'm sure you guys have some interesting questions to ask. So why don't we get started, kick it off. So talking about compression, we at least it seems that compression is a pretty important factor. We're hearing the hyperscalers talk about they're spending 3 to 5% of their CPU cycles in the data center just compressing, decompressing data. And then we're seeing compression on different processors, like Intel has a unified lossless compression on the GPUs. We're seeing compression on GPUs. We're seeing compression in the storage space. There's compression in SSDs, etc. And then on the other hand, there are companies providing IP, compression IP, like ZeroPoint. There's a CAST. So there's IP for compressing memory, IP for compressing storage. So it seems like compression seems to be pretty important, at least if you look at what's going on out here in the ecosystem. And now you have these new devices. It's not just the GPUs and CPUs. Now you have XPUs, you have CXL devices coming out. So that's what we'll structure the discussion around, to try and make some sense of compression in this new landscape that we are living in. And especially with the advent of deep learning and the need for having these humongous sets of data to which you train on and exchange data across multiple accelerators. So let me kick off by maybe the basic question, and maybe we'll open it up, start with Angelos and Heiner. Maybe if you could just briefly explain, what is, we know there's compression, there's lossy and there's lossless compression, but what is it about lossless compression that makes it different from lossy? And then if you could just tell us briefly about what are some of the key algorithms and flavors out there.
I can start. I guess the key benefit of lossless compression is that you don't need to have application knowledge, because you're essentially not losing any information while compressing your data, which is obviously the case in lossy compression. Lossy compression has also benefits. It can achieve much higher compression ratios, factors of 10 20x are easily possible there, but you do need to have the application knowledge. You do need to know what kind of audio waves you can throw away to compress your MP3 so it still sounds good. You need to know what weights you can prune in your neural network that it still works while being compressed. Lossless compression, on the other hand, always works with every data input. You're never losing any information. And maybe you can talk us a little bit more about the algorithms.
Something that I would like to add in the comparison of lossy and lossless is that, lossy, as Hanner said, can provide very high compression at the cost of accuracy loss and therefore the need of control. The challenge in the lossless compression is that it can be applied everywhere, but then some data will not be compressible. So it is the fact that now, when it comes to lossless compression algorithms, traditionally there are very known algorithms like QLC, that is one of the most common that we see. There we have Huffman, arithmetic coding. So there are a lot of different, and double coding. There are a lot of different compression algorithms, so usually we try to invent new algorithms, but we rely in the end of the day on the same methods that exist for the last 30, 40 years.
Okay. Maybe I'll pass this next question on to Mats and Scott and maybe Pulkit. So maybe is there can you provide an example of a real world application where lossless compression is crucial to have? Or in your mind, is compression, is it a nice to have feature or it's a must have feature? And go ahead.
Well, it's probably it's a must have feature for many applications. And if you actually go back quite a bit in time, but you may remember when you installed software with floppy disks. Well, when you got to about 20 floppy disks, imagine if data would not have been compressed on those. You would have maybe needed 40 of them. So there's really crucial for distribution and also distributing data. When bandwidth may not be sufficient to move data around. So that's definitely a need for compression. And lossless, well, my bank account, please.
Yeah, as far as, for example, an application like even a video compression goes, we don't know what the customer wants, so it's best to go with lossless. And for example, application is medical imaging or let's say a traffic camera on a highway, right? Something like that. There could be like fine details that you may be missing out if you do a lossy, and you don't know what the customer wants. So best to play it safe kind of and implement a lossy that works for all scenarios. That's my take.
Yeah, and I mean, I've been in the storage world this whole time, so I've had fun watching different ebbs and tides of the capabilities to compress and whether you do it before you get to the storage or after, have the storage device do it yourself. And from a perspective of where I've been from, it's really more of a matter of, is it already compressed or not when I see it? If it's lossy, it's sometimes you could even try to recompress it, but usually you can't lossless. There's absolutely nothing you can do with it, so it's just going to pass through. There's opportunities to do different aspects of it when it comes to getting into things like computational storage, where you want the opportunity to manipulate the data, and a lossy compressed data coming in becomes more challenging for a drive to do work on, for example. So lossless has better benefits given the fact that you might be able to decompress the data, work on it, and recompress the data before you send it back out. So there's pros and cons like everyone's kind of said, but really for the most part, from a lossless perspective, it offers the most opportunity for compressed data to be operated on in a computational storage world.
Got it, thanks. So maybe I'll bring the conversation back here. So of course, this is a storage developers conference, and we have the context of storage. So my question then is, now that we have CXL memory and memory is all over the place, and it is the most expensive component if you look at a data center layout, can compression be applied to memory? And if so, what are some of the nuances that you need to take care of when you talk about compressing memory versus at least what most people may be familiar about is taking a big old file and compressing it. So maybe if you could say a few things about compression in the memory domain, maybe Heiner and Angelos.
Yeah, I can start. So the key challenge. So first of all, starting from the question, the DRAM compression, we think that it is possible to happen. This is actually what we are working at 0 Point. I would say that the key difference between memory, DRAM, and storage is the granularity at which we access the media. And therefore, it is the granularity at which we need to apply the compression. So because the DRAM is accessed in the DRAM block, usually 64 bytes, then that is the minimum amount of granularity that compression need to be applied. And this is where the challenge starts, because at that small granularity, the compression ratio capability is low. It is not like a factor of 5 or factor of 10 that we have seen in the storage. It is maybe a factor of 2, factor of 3, something like that. So that is at least one key challenge. And then another key challenge that I could think of is the latency. The DRAM access is on the order of 50 nanoseconds. So whatever compression decompression you do, it has to be on the nanosecond latency.
Yeah, I think that's a great summary of where you can and how you apply compression on the per device level. Certainly storage and DRAM compression works well. Where I think it becomes a lot more challenging is if you look at the distributed cluster or data center level, where you have multiple systems that need to play well along with each other. Many of them using both compression and encryption. And in such a field, it becomes much more challenging. You can no longer simply compress and decompress on a single device. You have distributed services. Data is being compiled from multiple sources. And at this point, it becomes really the question of, can you still and where can you compress, right? Is it at maybe the user smartphone or somewhere deep into the data center? So there's a lot of challenges here to be solved.
So if I can add on that, so there's a nuance for memory versus storage. For example, for storage, you want to reduce both the effective bandwidth as well as the amount of capacity that this is getting. But for at least for some of our application, adaptive SoC or on-die memory, just for memory, we care more about improving the bandwidth, because we have enough capacity with LP and DDR, CXL, but what we don't get is enough local memory, right? So with compression, if there's a trade-off that we can make for maybe don't get the capacity benefit, but get the bandwidth benefit, maybe we're talking about even like 30-40%, not even 2x, 4x. That can get us to our next generation of what our next generation memory can bring us, right? So that's a very low-hanging fruit that memory compression can give us. And there are, of course, different challenges. For storage, you have more latency, but for implementing very close to memory, you get hit, as Andres mentioned, that we have very limited amount of latency that we can penalize using compression. So yeah, and that can play into what algorithms we can implement and where can it be applied in a SoC die, whether it should be on the controller itself, it should be before or after encryption, or Should it also take care of the on-die fabric resources? So all that needs to be taken into account in the actual implementation beyond the algorithm that's been chosen. Yeah.
Mats, would you like to add something?
Yeah, I mean, you mentioned before or after encryption. I guess before encryption,
Makes sense.
probably where you
Yeah.
want to do that, unless you have a very specific algorithm. But exactly for the bandwidth, I think that can be very beneficial if you can compress it with low enough latency and, of course, significant bandwidth for your needs. The other thing, of course, when you mentioned CXL, and CXL, okay, if you have once you start to have a CXL switch, and you start to move stuff beyond the switch, then you have multiple NUMA hops. And maybe if you could compress locally, the penalty is not as big as going yet another hop through a switch. So I think there may be some benefit for CXL to be able to compress in the CXL device.
Got it. Yeah, I guess then maybe a clarification. Just when we are talking about compression, maybe I should have prefaced the discussion with. It sounds like what you folks are suggesting in terms of latency and performance. It seems to me implicit that you're talking about hardware compression versus software compression is pretty prevalent right now. Like today, if I go and peep into a data center, most likely compression is happening in software. So the comments that you folks have made so far, how would you compare that to software compression? And Heiner, you mentioned some apps, if you're implementing lossless or lossy compression, then you need to be aware. So isn't it better to have that control in software rather than hardware? Just let software do all the compression, just using your CPU cores?
I mean, so maybe to get back to the basics of how most of these compression mechanisms work, it's essentially removing redundancy from data, right? So you look at different granularities of pages, of lines, blocks of whatever size. You're trying to squeeze out all the redundancy that you find and try to store the data with fewer number of bits without losing information. And all that introduces overhead. In particular, the more data you look at for removing redundancy, the more your opportunities become to get higher compression ratios. But on the other hand, it takes more time to analyze all these data for duplicate information. So these overheads motivate hardware support because hardware can accelerate that. But it's always challenging because it also removes a lot of the flexibility. You may want to apply different compression mechanisms based on the type of the data and the probability that you can find some redundancy, right? So software, you can easily implement all these things, whereas in hardware, you generally have to work on a very limited number of sizes that you look at, simpler algorithms, usually that will give you lower compression ratio, I would say, is my experience.
Yeah, and I think from to your point, hardware versus software, when you do commit to the gates in hardware, you also lock down to the point he was making around flexibility. So I'm going to put a compression engine in that does X, and all of a sudden Y comes along and it's 10 times better. I have to turn an ASIC to be able to make that work in hardware. So a nice combination of the two is tending to be where I would say the best way to look at it. And another great hardware opportunity from that perspective is going down the path where we are with things like UCIe and the chiplet direction, so that I can actually start doing. Today we have all kinds of one-off AI chips. There's nothing that would keep us from having one-off security chips, one-off compression devices, things like that, to allow for that better flexibility, giving you the hardware speed, but the software flexibility by way of that kind of a architecture and arrangement. Because once you commit to, say, for example, gzip, and all of a sudden I want to do something else, Z standard, I can't if it's hardware. But if I have a software algorithm that runs on a hardware core, I get 90% of what I would get from the hardware engine, but I do get that flexibility. So that's kind of how I would look at it.
Got it. Mats or Pulkit, if you would like to comment.
Yeah, I don't have too much to add to this.
Yeah, I mean, for storage compression, yeah, I guess it's a valid point, but I'll just like to add for memory compression, I guess it makes sense at least to do it closer to your accelerators if you have all those accelerators, because CPU may not be doing all that. So yeah, it's more, you will get, it's better to do it where your data flow is rather than taking the data up to your host and doing the compression in software there.
Okay. Let me see. I guess maybe I think some of you mentioned, or maybe Pulkit, was you mentioned about there's bandwidth, there's latency, and then there's compression ratio. Right? Sounds like these are the three vectors that you might try to optimize for when we think of compression. So maybe my next question would be, so how does, if I'm an architect, I'm architecting an SoC or an SSD or whatever it is I'm architecting, what kind of considerations do I make treating one off versus the other, assuming there's no free lunch, that I can't have all three at the same time? Maybe some thoughts on that.
So yeah, it's a clear trade-off in terms of how much compression we can get and how much latency we are willing to penalize. So I guess it depends on how much we are after. If our clear goal is, let's say, bandwidth, we are probably not after a 10x improvement on a memory bandwidth, because you'll be hit by your DRAM throughput anyways. So maybe if you can get to a linear increase, and with that linear increase, making sure your latencies are not getting penalized more than 10%, maybe 9-10 cycles. And area is also important here, especially if it's done on a dedicated hardware accelerated compression IP. So area is also important, and that kind of plays into how much engines of compression we want to have to amortize the latency impact and how much throughput it can give. So in my opinion, we can sacrifice the amount of bandwidth and storage or capacity benefit we are getting, but make sure we are not sacrificing latency and area beyond, let's say, a few hundred kilogates, something like that.
So one consideration is, of course, I mean, you mentioned SSD. Well, SSD and memory, there's about 3 orders of magnitude difference in latency. And for SSD, we typically work with bigger blocks. So of course, there you have much more time to do a compression. And the throughput can actually be significantly improved. Because if you could compress something by 10x, and you could effectively get a throughput that's approximately 10x higher at very limited latency increase. So that I think would be very interesting. But then the problem is it worth? Is all data you're storing compressible, or is the majority of data non-compressible? That's kind of the question. Do you want to make the investment in the hardware for that?
Yeah, to kind of add on to that, especially from the storage side of that, or from the physical space perspective, for example, if I'm not in control of the absolute workflow that's going into the device, I don't know if it's 2-to-1 compressible, 1.2-to-1 compressible. I can increase the bandwidth capabilities if I assume a certain amount of spare space, right? Think of it as funky overprovisioning to some extent. And then I don't really care what the user's data is compressible or not. I'm focused on the latency or the bandwidth. The capacity is going to be what the capacity is going to be. I can't simply say a 16 terabyte drive is now 32 and guarantee it. There's no physical way to do that unless I'm 100% in control of that exact data set that's going to it. So if I'm looking at it from a data center or from a colo type perspective for someone who's got a general purpose server that's letting many users on it, I can't guarantee you capacity, but I do have pathways to guarantee you bandwidth or latency, whichever type of trade-off you're willing to make. But the capacity of the device is never going to be presented as 2x. It could even end up being presented as slightly smaller than the physical capacity to allow that guarantee of bandwidth and latency.
Interesting. Any other thoughts? Or yeah.
Now, maybe just to add or stress that it is so application dependent, the amount of compression that you're going to get. And unfortunately, when we design SoCs or hardware, we usually don't know what kind of applications are going to run. So that's why I think we need a lot of flexibility in the hardware that we're building for compression. So hardware, software, co-designed approach, which gives you enough programmability that's needed.
Yeah, and if I can add, you mentioned earlier that usually it's not one algorithm that is the best. So when you're building an SoC, because it is in hardware, I think that it is a combination of algorithms. Yes, there will be an area trade-off, but we don't need to have like 5 different algorithms, but maybe 2. And with hardware, software co-design, I think that it is going to be feasible.
Fantastic. So I think we are about the halfway point. So maybe what I'd like to do is turn it over to the audience. If I already see one hand up there, but yeah, if you have any questions, and then we can come back to the originally programmed, scheduled questions. But go ahead. So first question.
So Nilesh, it's actually for you. You cited initially something like a 3 to 5% use of conspiracy. Right. Where'd that number come from, and is it broken down by anything else, specifically since the storage conference? How much of that was storage?
Oh, yeah, great question. So this is actually from published papers by Meta and Google. So they've published the amount of CPU cycles that go into compression. I believe the analysis applies to storage compression, the 3 to 5% of the cycles. So, and I believe, yeah, they gave a breakdown of all the algorithms and what proportion they're being split up into, like Z standard or Snappy or whatever, gzip, etc. So that's where the reference is from. I can provide you the links off.
Yeah, actually, maybe even put it on a slide and we can add it into the slides.
Sure, absolutely. Thanks. Other questions? Anyone? Yeah, please.
One of the great fallacies is bandwidth is 1 over latency. Not really true. And so my recollection of the level set algorithms is you had to try to do a test run with your data pattern because it might actually expand the data. So you have to keep the original data, run it through the compression, and then choose either the old data or the new data, which then increases the latency. Is that still true for LZ algorithms, or are there LZ algorithms that just don't run the risk of ever having an expansion rather than a compression?
I can comment.
Question.
It's a great question. So the question is if the LZ algorithms can expand the data and therefore this will have an impact on the latency, correct? The answer is yes, actually. The level zip can still expand the data. It is still true. And that's why, at least for DRAM, and when we target to do, as I said earlier, for DRAM block compression, for bandwidth acceleration, level zip would not be an option because of this limitation.
Any other comments?
Yeah, no, I think you answered the question.
Okay. All right. Oh, I see. Go ahead. You were first. Question.
So, compression results in variable-sized blocks. How these blocks are organized into blocks?
So the question is, compression creates variable-sized blocks. So how do they get organized into a device? And I would say, like, a perfect example from a solid-state drive is we use a caching algorithm to do that for any size data coming into it. So from a allocation of space, we'll consume an adjacent, create the adjuncts of all the different blocks to the right page sizes that we need or block sizes that we need to submit them, just like we would if it was an uncompressed data stream. So the size of the packet, if you will, doesn't really matter once it hits the device. It's all being managed in the memory piece of that, even at a drive level. If it's coming in as raw data and the drive is doing it, you're going to see it compress it, realign it, and send it in the right block sizes. If it's coming in from the host as pre-compressed data, it's still going to be variable block sizes. We can still append and concatenate as necessary.
So you stop multiple compressed blocks in the same single block.
If the data aligns appropriately, you could do that, yeah.
So what happens if one of these blocks is really one of the compressed blocks? The RDA is really.
Yeah, so the question, the follow-on is if you end up needing to rewrite a block. Again, it's all zeros and ones to a drive level perspective. I'm going to empty a block into memory, erase it, and recommit that same amount of data plus the new data that I'm replacing it with into a new block. The drive doesn't care. The device doesn't care from that perspective.
To your point, and that if you stick with 4K blocks only, of course, assume you can use a smaller translation layer. So there is some cost to having variable block size.
Yeah.
So it's not completely free. So if you 4K block size, your translation layer is pretty well defined and it's easily defined. If you now start to have different sizes, yes, you need to basically increase your memory of the drive. But of course, you also get more storage.
Yeah.
Yeah, one follow-up comment that you need to store that information, how many blocks you're putting into one page or super block somewhere, right? So that's why every compression mechanism introduces some metadata overhead that you have to store somewhere, which is also why in the worst case you're increasing the storage and you're not really decreasing it. So somewhere you have to store that information. That's why you generally restrict yourself to a certain number of block sizes that you can support. You won't do that too dynamic, right?
Okay, I see two hands, but I think, Matthias, you were first. Go ahead. We'll come back. Actually, we'll come back to you. I think he was next.
What's your thought when end-to-end encryption is needed? Like, what's your thoughts around this kind of that's needed? And you can do compression on the SSD side, you have to do something else. Is this kind of a solved issue in practice, or is this kind of something that's nothing, compression in general?
Can you repeat your
The question was, what's the impact of end-to-end encryption on compression, right? Which pretty much every hyperscaler does today. They want to encrypt the data as early as possible, if on the user device, basically, so that it's protected not only on the storage media, but also when it travels the network. And when you do encrypt, you can no longer compress because the data, the entropy is just too high. So the question was whether this hinders compression. And I think it is, in fact, still the biggest problem that prohibits us to use compression everywhere. You can do it on the user device, of course, before you encrypt, but then you're limited in, you can no longer implement it in your CXL or SSD that sits in the data center.
If I can add, yeah, that's actually true. And if encryption is good, then compression will not be able to do anything. But on the comment about the CXL, there is encryption support on the CXL, for instance, but that is on the link, right? So if the encryption is applied just on the link, then there will be opportunity to do the compression after, because when the information is transferred on the device, it will be decrypted. And then compression opportunity is possible again. So it will be hindered only if the encryption happens by a component, for example, on the host, and leaves in encrypted form, and it will never be decrypted on the way to memory and to the storage. At that point, yeah, it will be totally hindered, I think.
Okay, I think, yeah, question on the back.
So one of the things that was common in spinning hard drives was the ability to offer guarantees for space provisioning. Have you guys thought about cannibalistic storage in the sense that I can have multiple namespaces such that I can identify what namespaces have provision in case I start running this space? So I can do that on a subscription process.
Okay, so if I repeat the question, you're saying how does namespaces?
So you've got to guarantee the space, right? So if I can't guarantee the space, can you have multiple namespaces and have one of those namespaces be set some kind of a high-speed area that you can work with? that you can identify as sacrificial and these things go bad. In other words, could a consumer identify what to throw away so you can continue operating with your own problem? Have you guys thought about that?
Yeah, so kind of my version of a summary for the purposes of the recording too. So basically from a capacity guarantee perspective, you create namespaces that are sacrificial, that I don't care when I need to fill space, I'm going to eliminate a certain namespace because I know it's data I don't care about, so that I can continue and path forward with the compression and things like that to ensure the data size is correct of the device. I would say from a perspective of what I know that's going on in the space, it's still something that's a challenge. And there's work being done in several different standards bodies to understand how to manage that. I know there's been things that have been pushed into NVM Express, for example, that have started and stopped a couple of times around how to manage that. But I don't know that it's figured out just yet.
All right, there was a question up front, out here.
Oh, I have the same question.
Okay. Oh, one more question.
I think we all kind of agree a level Z style storage born compression has got a lot of messiness. How about dedupe? Is there any opportunity to do, I've already stored this file, I don't need to store it again, and I got it then with certainly with the world of hyperscalers, probably the same thing is uploaded thousands and thousands of times and stored maybe thousands and thousands of times. So there's a way to maybe accelerate dedupe at a host level as opposed to just levels compressing the same file 1,000 times.
Got it. I'll just repeat the question. So your question is there an alternative to compression in the form of deduplication? And could it be a valid substitute? So maybe for the panel. Any take it?
Go for it.
I mean, it's definitely a valid substitute, and that's. But I guess your question more specifically is it possible to accelerate dedupe, and it is. And
I think there's dedupe going on anyway. The question is what you solve.
yeah, no, I mean it's definitely possible to accelerate dedupe, and I mean part of that has been part of the computational storage effort. It has been accelerating dedupe, and so that's, I think, if I'm not mistaken, part of some examples in the SNIA spec.
Yeah, I mean, there's opportunity there for sure. How it ties into end-to-end encryption plus this plus that, and how we can make it all work together is still not quite clear. Because I think one of the most overlooked aspects of everything going around is in the development of the front-end host-based stuff is storage is just storage, and I can't do anything but be storage. And we still have not, even with the efforts of 5 years of computational storage development work in here and in NVM Express and everywhere else, people still look at a storage as storage as storage. And you talk to an end developer, and usually storage is just a location. They don't even know what it is. I mean, there's multiple papers that have been written on really cool stuff that it's just not fast enough, and they're using old spinning Rust, to Chris's point, versus even an SSD, and not realizing that because they just didn't know any better. So I think there's a lot that can still be done in the storage space to better help people understand that you can do more with storage, whether it's computational storage or just realizing the differences of the activity you can do with an SSD type product and or a CXL memory based type of product.
Storage devices don't even understand files stored on a storage device. They just understand LDAs. So
Exactly.
you're going to have to potentially start drilling into what is actually on there.
Yeah, and I mean, there was a historical startup in the 2007-8 timeframe that tried to do something like that and never quite got off the ground. So we'll see if it comes back around for sure.
And actually, just a follow-up question, do you need to pick one or the other? Is it dedupe or compression? Or can the two coexist and give you even higher benefit?
You can do both, right? One after another. I think when you to compare the two, you will often find at least a little bit of compression opportunities in almost all data that you find out there. Dedupe is, I think, sometimes, I mean, the canonical example is always running multiple VMs on a machine that have truly duplicated data pages. Then those are a great opportunity. but then often you won't find anything. And the process of figuring out whether you have dedupe opportunities is often also higher, I'd say, than with compression. You have to look at data over larger time frames to compare for exact replication. And so I think compression is probably the first one to tackle, maybe. But then, yeah, there have been also hardware accelerators for dedupe before.
Did you want to? Yeah.
Yeah, I would say actually that I would try the other way around. I would try first deduplication, then compression, because usually deduplication, it looks at a larger granularity and then across a lot of data, right? So you try to get rid of all the duplicates, and then when you have the duplicates, try to compress those duplicates in another way. But I also see the challenge with the duplication, which is that it depends actually how you implement, how you back reference to that unique copy, and what happens if you start modifying that, then it becomes quite challenging.
Okay, maybe I think Kapil, you had a question up front here.
I'm just trying to understand, get an intuition of how do you match the algorithm to the data. And I think ignore the challenge that, okay, data is with hyperscalers who are not going to give you the data, so you don't know what algorithm to apply or algorithm to develop with research. But in general, like, I'm just trying to get a basic intuition, like, why would you do LZ4 versus vScatter versus some other compression? How do you figure out, like, what is inherent in data that this algorithm is fundamentally better in data?
Anyone?
Well, I'll at least repeat the question just for the benefit of the camera. So the question was, how do you determine which compression algorithm matches the data set that you're dealing with if you know what the data set really is coming into it? And he made a comment that CSPs, for example, won't let you see the data, so how do I know what to do with it type of thing. And I would say that one thing that is being done in that space is that's what kind of some of the standardization work is being done, or open standard work, i.e. Zipline that was introduced by Microsoft at OCP is an example of them trying to drive people to a direction. Whether it's the right perfect thing or not, it's just a generic one that they say, here, everyone should use this so you can at least get to a common ground. Because there is, to what we kind of all said a little earlier, there's no real easy way to do that. And the amount of time it would take even for an intelligent drive to figure out what it is to apply the right algorithm is still a considerable amount of latency up in the front of how long that data stream is actually going to exist.
Okay, one more question?
Maybe one more. So most of these compression mechanisms really care only about bits, right? So they don't really have an understanding of what kind of data those bits are representing. So even if you could have some rules, like if you have image data or whatever, you should use this kind of algorithm, there may be some change at one of the levels in your software stack that completely change the bit layout on your storage media, and then suddenly another compression mechanism becomes maybe more applicable. So I think it's hard to say, to give you a recipe of what algorithm you should use.
Just basically some experimentation to see if you apply all of them and then figure out which one it is.
Okay.
Try all. That's better.
Well, I mean, there is also another aspect, which is, for example, I mean, what is the sort of the data redundancy? And there are not so many different sources. Either the data will be close enough in value and their delta encoding would make sense, or they are like replicates. And then there's another technique, that's dictionary-based, for example.
A little bit my follow-on question is, so we have block-based comparison. We have all the usual guys that does different algorithms. We're going to use the same algorithm for byte-based kind of compression, where we have to compress hash line or something like that, where it's like much smaller like amount of information that we have to compress. So that's that. And then, I mean, do they need different algorithms? And then do we need new standards for now that we don't do blocks anymore, we do bytes? Do we need to go into standard bodies and do new algorithms for like byte-based compressions?
Oh, great. Let me repeat that question. So your question is, do you apply the same algorithms to storage blocks as you would now to, say, cache lines in a memory space? And then are the algorithms need to change, or do there need to be new standards, or can it be the same? So maybe we'll open it up to the panel. Any thoughts?
Yeah, as I mentioned earlier, yeah, it's like you can't really apply the storage algorithms directly because of the latency area. You have to pick and choose some of the features. Yeah, I know there's no standard as such for at least for memory or cache line computation. It's a fairly new area of research. So, but what as a SoC designer, you would know what are the bottlenecks that you want to solve, how much is the bandwidth improvement you want to get, how much is your area budget. So with that, you evaluate on a hardware acceleration which algorithm can achieve those targets. And then if it's just one that's giving you the answer that you want, you have to choose that. It could be like maybe arithmetic encoding doesn't work. Huffman, some part of it could work. Maybe wavelet transform is too expensive, it requires too much floating point calculation. You do some simple bit plane compression and try to get it to work. So all those things you have to keep in mind, assuming your hardware resources are limited and on-die hardware resources on SoC are limited, and make a judgment based on that. Yeah.
But with a larger block size, you can of course compress more efficiently. And if you go to cache line, yeah, maybe not as efficiently. So yes, you would need different algorithms.
And I think as long as you're staying with bytes or lines, you're probably talking about a hardware mechanism. So you have your mechanism coupled in a hardware block, right? You don't have to expose it to other people or software. Then maybe you don't need a standard.
That's what we're here for.
All right. Any other thoughts? I think we have like 2 or 3 minutes, but I think, yeah, one more question. Go ahead.
So right now, an application knows that whether or not it's ready to compress data, say compress video. A file system, you know that it's writing all those blocks encrypted. Right now, we throw away that information and then let the lower layers try to figure that out again. You don't need blocks to send that information down as base.
So I think if I summarize the question, the higher level applications have a lot of additional information or metadata about what the data consists of. Is there some way to pass that data down to lower level hardware engines which may not have system level awareness? Any thoughts? And would that actually matter? I think, Heiner, you made a point that it may not matter, at least from what I got, but maybe other thoughts like can we, first of all, can we pass this info down, and would it matter? And I think that's our...
We got a 5 minute.
5 minutes? 5 more minutes. Okay, great. Go ahead.
It impacts power usage too, not just latency.
The question was, how would it impact not just latency, but also energy? How would it impact energy?
I would say I think there's certainly opportunity to do that. It's something that I don't think people are truly looking at the full system architecture level today. It's something that people need to do a better job of figuring out how to make the lower levels that much more intelligent. And I think part of that came down to we didn't really have a secure path to transmit a lot of the data that we were doing from point A to point C to point D. And now that we're getting all these things like link encryptions and the encryption on the link on CXL and other ways of attesting the devices to make sure they're legitimate, we can start being more willing to share that information further down the chain too. I think a lot of it came down to where can I hack it? And if I can make it unhackable, then I'm capable of sharing some of that more pertinent information to make it more valuable downstream.
One question? Yeah, go ahead.
Yeah, so I guess the question about compression for data and memory. So, I mean, and related to compression ratio and latency. So what compression ratios can be expected for data and memory when we talk about 64 bytes per given? And then the second question is, what's the latency over, for compression and memory?
So I'll repeat the question, which
it would
is,
be good to get like some quantitative data here.
got it. I'll repeat the question. The question is, when you apply compression to, say, cache line data or 64 bytes, first of all, what is the compression ratios you can expect? And then I think your second question was, what is the latency you can expect? So, any takers?
I can take the question since I have quantitative data off the top of my head. So if you take a simple algorithm that has a latency of just one cycle, then for datasets like databases, you can expect a compression rate of about 1.5 at most. If you go to maybe 3 nanoseconds, you can go to a factor of 2. And if you are willing to go to maybe 5 nanoseconds, then you can go even to a factor of 3. And this is with 64 bytes.
Okay, and I think that wraps up our time. So I just want to thank the panelists for taking the time, share your thoughts. Thanks for all the questions.
Thank you.